Today, I want to start again reminding you what I was talking to you about this Tomita Takesaki theory, but I am trying to do it in finite dimensions because of technical problems which arise in infinite dimensions. But mostly, these technical issues can be set aside when you do actual calculations. And so, I can say that if one enters this quantum field theory at this level, there are a few words you should know. One is certainly GNS construction. You should know. Second is this Tomita Takesaki theory. Third is, if you want to really impress people, you can also talk about cyclic and separating backward. Okay? And if you tell people appropriately with your friends, it's very likely that you will be invited for an opening talk in some big conference. So keep it. I would say that you should know this. So these are so common that we should understand what they mean. So, so the thing I want to the basic the reference from which we develop this theory. I given the book is by Baumgarten and Wallenberg. It's rather a thick book, but I have given the exact place where the finite dimensional Tomita Takesaki is worked out. It's actually given as a problem, but one can follow and then develop it. I'll give all the details now. Okay? So what we have got here is we have got an M by M matrix algebra, and we want to start with the density matrix rho, which is and make a GNS construction. Okay, so we will construct the Hilbert space from the density matrix. And for convenience, we will assume that this density matrix is cyclic and separating. Okay? So, no, density matrix is non-singular. That's the correct way. So, non-singularity means that is all these eigenvalues are non-negative. Okay, so it can be written as rho equal to, if I write the spectral decomposition of rho. If I write rho in a spectral decomposition, the AI squared comes to 1 because trace of rho is 1. And furthermore, all the AI are real and positive. Okay? So we can write rho like this, okay? Because its determinant is not zero. And then we can, and these F size are orthonormal vectors, so we have also this equation. Okay? Now, I want to make a GNS construction. So what we have to do is to first define a Hilbert space, at least an inner product space. So each vector is labeled by the matrix of the algebra itself. Okay? So each vector state is labeled by an element of this capital M. And the scalar product of two vectors is given by trace of rho times M star M. Okay? I don't write dagger and write a star because certainly mathematicians use star all over the place. And in the physics literature also, star is more common than most, at least the emerging physics literature of this kind. Star is a more common notation. So I will use that. So the scalar product of two matrices is given by trace of rho times M star M. Okay? Now you may remember that the first step is to check that there are no null vectors. Okay? So what that means is, suppose this trace is 0, what can I say about M? Okay? I write it down. This equation is this equation, where A square are all non-strictly positive. Okay? So we know that this is summing is, if this is 0, the sum is 0, so each term is 0. Okay? So each term is 0 means that you have to get this equation M fi times scalar product of M fi, that M fi is 0. Or it means because M is annihilating every vector fi, so the norm of M fi is 0. So M fi is a 0 vector. So that means that this M annihilates each vector. So M annihilates each vector, so M itself is 0. Okay? That means that this equation, the null space consists zero norm consists only of zero vectors. So there are no zero vectors for this row. It is good because I don't have to worry about quotienting or zero vectors. So let us go. So there are two properties which follow from this equation. One is that there is something called a cyclic vector. What is a cyclic vector? I'll tell you what in this representation. That in this case, what it means is that there is a vector. That canonically, this vector is labeled by M. Notice that every vector in the Hilbert space is labeled by an element of the algebra. So I label this by 1. Okay. What do I mean by cyclic vector? If I apply all the elements of the algebra here, I get the full Hilbert space. Okay. That's what it means. Okay. For example, in the vacuum, you take the vacuum in quantum field theory and take any local algebra or even algebra all over the space. When you go on applying all the operators, you will get all possible vectors for the Hilbert space. And this is also true for local algebras. And yeah, it's also true for local algebras because of a theorem which a few years ago I proved here, and I'll prove it again here, called the Risch-Taylor theorem. So, certainly in the Fox, when we construct the Fox space with creation and annihilation operators, this is true. So, in this picture, one is a cyclic vector. Because if I apply the algebra M, I get all vectors, all M by M matrices labeling the get vectors. So I get the full Hilbert space. Okay. So one is a yeah.
I understand that the AI square should be equal to
A is a real numbers because the AI squared are the real eigenvalues of a self-adjoint operator rho. So they're all positive. So I take the positive root. A squared is positive, so I'm here considering the positive roots of AI squared. Okay. You get similar with it. Yeah, it's convenient to take the positive roots of AI squared. So that's what I have done. Okay. By the way, if there are people listening to me on Zoom, I suggest that they ask questions. Okay? I request you to, those who are listening and have doubts, the Zoom talk, please ask. At least highly the students from Hyderabad suggested they may listen. So there may be one or two people, so they can ask questions. Okay? Otherwise, I don't see any place for the chat box. So I cannot recognize the chats. Okay? Yeah. Maybe we will come back to it later. Okay. So there is this expression I am taking as a cyclic vector. Okay? That is, I can generate the full Hilbert space by acting with elements of the algebra. Okay? It is also a separating vector. What that means is that if I apply any element of the algebra, it is non-zero. The vector I get here is non-zero. That means no two vectors which are non-identical in the algebra, their difference is a zero actually on the vector. So that means it is so it separates the state you are taking here separates the vectors. Okay? So here also you can see that is the case because if two matrices M1 and M2 and is 0 on 1, M1 minus M2 is 0 on 1, but we have already proved that M1 minus M2 is 0. Okay, so M1 equal to M2. Okay? So this vector is what is called cyclic and separating. Okay? And now, say theorem which is not difficult to prove, and you look at the proof, it's to me at least it was a pleasure to look at the proof. It's a trick proof. Okay? To show that if this vector is cyclic, the operators which commute to this the commutant of this algebra, that is all the operators acting on this Hilbert space which commute to the algebra we are looking at are separating and vice versa. There is a duality. One is separating means other is cyclic, the other is cyclic means so we have a exact duality. So since this is cyclic and separating, the things which commute with them is also cyclic and separating, and we will see it explicitly. how to find these objects that are commuting with this M. Okay. Now you may ask, what is the physical meaning of this M prime? Prime normally denotes the commutant, and you may ask what is the meaning of it? What are they in physics? Okay. We will see later. Then in physics, M will be some local algebra, and M prime will be is
Hi, Bal.
Yes. And
Bal.
yes.
Yeah, so Pramod here, Bal. So, Bal, your slides are not changing. A few of us are online, and it's not clear to us whether you're using the Blackboard or.
I'm using only the slides.
Okay, but your slides are not changing. It's stuck to us on the first slide.
So I am on this slide. Can you see the bottom page 4? Can you see?
No, we are seeing the first slide, which is the title slide along with your name.
அது நீங்க தான் பண்ணணும்.
Yeah, we are not able to see the change slide.
Yeah, you probably will attend to it right away.
Yeah, so I actually want to ask you one question about the cyclic vector.
Okay.
So is it possible to have other cyclic vectors which are not the identity? Like for some algebra, can you have a cyclic vector which is not identity?
Yes. Yes, that is correct. Even here, the only thing, let me just see. If you take any vector which is, you label any vector with a matrix M. Okay, so take the vector with the matrix M, which is invertible. Those are all cyclic vectors. So, I mean, the Hilbert space your vectors labeled by ket vectors with any matrix is invertible or not invertible, and one can easily show that if the ket vectors are labeled by invertible matrices, they are all cyclic and separated. Okay. So there's a plenty of them, but one is convenient. There's canonical choice, if you like. That's what naturally comes up, so we use that. Okay. Hello.
Yes. Okay.
Can you see the slides now?
Yes, we can see slides now. Yes.
Okay.
The first page, yeah.
So shall I go on?
Yeah, sure, yeah.
Can you see the movement of the slides? No, I am on page 5. Can you see it?
Yes.
Yes.
All right. So I want to write this vector, the cyclic and separating vector, essentially with a different notation, with a notation which is convenient. Okay. And it seems to have originated with Umezawa, where he was doing finite temperature field theory. I don't know how he got into this, but he did write this double Hilbert space I'm writing when he was doing finite temperature field theory. And somewhat later, Ojima interpreted his work, Umezawa's work, in the language of Tomita Takisaki theory completely. So there is a paper by Ojima, which is quite readable, which actually interprets the work of Umezawa in finite temperature field theory in this language. So you may want to look at it. It's a nice paper. So,
Which year?
it was sometime in the 80s or something. You write Ojima. Ojima is very well known for his work on BRST and so on.
So this paper came out after Israel's paper on something.
This guy, whose paper?
Israel. The other paper on thermophile double, like which describes the purification.
I don't know these papers. The paper I know is Ojima. Well, once you know this work on Tomita Takisaki, you would start guessing that that's what Umezawa was doing. And Ojima went through the calculations systematically and showed that we will see what it is. Something called a anti-unitary operator, which will come up now, is actually CPT in his Ojima, in Umezawa's formulation also, okay, which was shown with an independent notation by Bisoniano and Rickman. So has been a convergence of points of view in the 80s and the 90s. It seems to have passed by people doing functional integrals, which is a shame. These are beautiful things, and I think address several foundational issues. So one should know these things, in my opinion. Okay. So let me go on. So I want to write. This row, the density matrix is in terms of a vector state, and the expectation values I am looking at in terms of a standard vector state. So what Umezawa did was to double the Hilbert space. That's what I said last time. And so you have the basis here, and I'm going to write this one in my previous notation as denoted by omega denoting the vacuum meter, right? And I write it as Fi, the basis we have already had, tensor with Gi, which are all unit vectors in a auxiliary Hilbert space. So I've enlarged the Hilbert space. I'm working with tensor K, okay? And I'm writing this vector here. Okay? And the AI are the positive roots of AI squared. Let me take this vector. Okay? Now, if I take the expectation value of any observable here, M, this M acts only on the Fi, doesn't do anything on the Gi. Okay? So the operator which I call M are some M cross unit operator in the K star. So it only acts on the Fi's. So what happens if we take expectation values? And so let me see if I given the equations. Yeah, I given the equations. So any M of the observable algebra are linear operators on the first Hilbert space, tensored with say complex numbers multiplied by 1k. One is means identity in the second Hilbert space. These are my observable algebra. There is another algebra which is 1 C times 1 on M, the first Hilbert space, 1h, tensored with some operators F prime acting on from the other side. All the matrices acting on K. But I am looking at this one. So I will it also here, the second one. And you can see immediately that the expectation value of M in the state I wrote down is exactly what we want. So what happens? Yeah. And this is my vector, and I am taking this observable algebra is acting only on the Fi's. So when you take scalar product, the Gi, Gj, the cross terms will give me delta Ij, and we take away all the cross terms will disappear because of the fact that Ga and Gj are all common. So I not equal to J. And I get back the formula that the expectation value I'm getting is AI squared times the expectation value in Fi. So this is Umezawa's trick to go from here to the standard scalar product. And why was he interested in this? Because he can create both the Hilbert spaces with creation and annihilation operators. Okay? So he can introduce a creation and annihilation operators for the first slot and for the second slot, and you can start writing fields accompanying these creation and annihilation operators, which is what he did in his original papers, and also in the book he wrote with Takahashi. Yes, and there is a tradition of following Umezawa has been a tradition in Hyderabad by Srinivasan, V. Srinivasan, who was in Hyderabad for a long time. Now he's retired. He used to be an enthusiastic sponsor of Umezawa. But let's go on. Let's go on. So I want to show now that in this way of writing also, this vector I am writing is cyclic. Okay? It is slightly tricky and it is a useful way of doing it because it will enable me to find this, prove this theorem of Tomita and Takesaki. Tomita and Takesaki. So let me do that. Okay. So, and show also some very important property. So I am going to define in my matrix algebra an operator which I call AJS is a matrix, n by n matrix labeled by J and S, and it lacks this vector change, and the answer will be delta JP times Fs times GL. So it doesn't do anything to GL, it only changes F to F, FP to Fs. So it is an operator. This in the matrix algebra I am interested. It doesn't do anything to the second to get this. Now, so it is changing the original vector. So let us see what it does to my vacuum vector. So I want to know what happens to the vacuum vector. It won't do anything to GI, okay. But it will change this act. It's a summation on I here. So I get delta Ij times Fs. So I got Fs here, and the delta Ij will take this Ai to Aj and Gi to Gj. So the result of this operation is this operation. Okay. And these Aj's are not zero. Okay. So I can get any S and J here by simply changing the A's. And the A's are in my original matrix algebra. So I get the whole set of vectors like this with Aj non-zero. But these are all this is exactly the basis of the full Hilbert space, because I can get any S and J here. So if I take linear combinations, I get all vectors. So you see that this equation proves right to me that the vector I am looking at is cyclic. Okay. The Umezawa way of writing purification is cyclic. Okay. You should, because I am getting I am getting the entire basis vectors. So by linear combinations, I get all possible vectors in that vector space. So I am done. There's one point you should notice right away, which is going to be important. Where is the this GI is a basis for the dual vector space, okay? Any orthonormal basis. So there is an ambiguity in the choice of the GI. I can change GI by unitary operator to any other GI, G prime I. Okay? This won't change the answer, which means that this operator I wrote down I have said it here quite explicitly. This operator I wrote down AJS. Okay. Sorry, you to be patient because I have to be, This operator I wrote down is not unique, because every time I change the dual vector, I'll get this operator AJS is changed, okay? Because it is acting on a different vector. So I should label this AJS by the basis. Okay? And if I change the basis, I get another AJS. So if you take this AJS for one G, say G tilde, and act on the first one, it will not be it will not act in this way. It will become something else. Okay? So I can the equation for AJ, this choice of AJS is not unique. If you look in recent papers on this modular operator, you see they talk about relative modular operator and so on. For example, in the calculation of entanglement entropy in quantum field theory, it becomes important. So, what is the relative modular operator? It is the one which is constructed from the fact that I can, in this finite dimensional language, corresponds to the fact that there are several different choices of G's. Okay? And this is related to my PDF, where I talked about entropy increase. That is related to this type also. And there also, Araki shows, when he discusses relative modular operators, that there is a monotonicity property of this relative entropy. Okay? So they are all relative. Okay? And they are all coherent. Okay? The second equation I need to know what is adjoint of A. Okay? What is AJS adjoint? Okay? That you can also calculate, because I use the definition. I take a basis FP cross GL, AJS, FR cross GQ, and I ask what is adjoint to this? Adjoint element is acting on this with the scalar product, the two things get to be equal. So what this is say about adjoint? And the proof is that AJ as adjoint is simply ASJ. The thing is, see this from here. For example, this object here is delta Pj Fs. So delta Jp I get Fs. Here I get Fs and I get Fr. So take delta Rs, then delta Ql. On the other side, you will get, if I add to this, I get delta Rs again, which is this one. Then I get Fj with Fp delta Jp, is this one. And I get delta Ql. So it is the same. So the adjoint of AJS is AH. This is also an important equation. So we have got a set of matrices acting from the left, which generates the full Hilbert space. And using this, you can also check that. This is by the same technique, you can find an A prime JS acting on the right by the same similar equations that will again generate the full Hilbert space. The calculations are essentially the same, changing indices. Yeah. So you find there is a AJS, a set of operators acting on the left, generating the full Hilbert space, and a set of operators acting on the right, and generating the full Hilbert space. And the vector I have chosen is non-singular for both of them. Is non-vanishing for any vector in the matrix algebra. Okay. So here I have got the equations. Yeah. Now, given these circumstances, so what is the circumstance I am dealing with? What I have shown here is that the vector I have chosen is cyclic for the algebra of matrix M and the algebra of M prime. Notice that the algebra M prime acting on G. The algebra M prime A prime is acting on this G, not on F. So it will definitely commute with M. Okay? The original algebra acting just on F. So this is a commutative algebra I am looking at. So I got a vector which is cyclic for both left and right algebras, or it is cyclic and separating for any one of those algebras. Then comes this theorem of Tomita-Takesaki that, and this is the central theorem, which actually happens to be correct also in infinite dimensions. That is quite non-trivial, and I'll prove the theorem in finite dimensions. But you should be aware that this theorem does not apply for the vacuum vector for the full Hilbert space on all of R3. It doesn't apply. It applies only in quantum field theory. It applies only to the local algebras. Does not apply if for the Fox to take all creation and annihilation operators. It is not true that this equation is correct. It is wrong. It's simply wrong. And I think I remember Krishna asking a question. You can quite easily see, because in the full algebra on space-time spatial slice, you have the number operator. Okay? But you may object number operators has a huge eigenvalues. So what do I do? Take exponential I times n, where n is so it's a unitary operator. So if the occupation number is k, take a vector in a Fox space with occupation number k, then exponential in will have eigenvalue exponential ik, right? So exponential in is an operator with eigenvalue exponential ik. So you take exponential in minus exponential ik. Okay? Both are exponential ik is simply number, complex unitary number. Okay? That acting on this occupation number state k is 0. So it is not separating these two vectors, and this is true for every k. So there are infinitely many vectors which are not separating this, which I can find like this. So the theorem does not apply in full Fox space. Okay? If somebody comes along and writes such equations, the full Fox space is wrong. It is not correct. Whereas in the local algebra, there is no way you can average a quantum field and get creation and annihilation operators. Okay. Because you to get that you have to multiply by exponential I k dot x and integrate on all of x. There is all of x is not available for you for local algebras. So in those cases, it happens that the vectors you choose are cyclic and separating. The vacuum vector is cyclic and separating, and that has very deep consequences, which I will tell you as we keep going. Okay. Any more questions? Okay. So, what Tomita and Takesaki proved is the following. Tomita proved, I think Takesaki wrote it up, or I don't know exactly. He said, under this condition, the Tomita and Takesaki says, and I'll give you the details, that there exists an anti-linear involution. S, which is called S. S is anti-linear operator, is an involution, that is S squared is 1. It is not unitary. It is never unitary. But S squared is 1. It is anti-linear. So when acting on complex numbers, it makes complex conjugation of those numbers. It's like a time reversal operator. And it is defined by the following equation. Take any matrix M and act on my vacuum vector and act with S. The result is M star acting on omega, on the same vector. So, so S acting on omega itself is 1. You see that that is correct. So on the vacuum, this S is 1. On other vectors, which you can obtain by applying M on the vacuum, it changes the vector to M star times omega. This is what Tomita proved. And then he proved, in religious context, Bisonen and Bickman did the following. They took this S and did the polar decomposition of S. Okay. So normal matrices, the polar decomposition means that you take the square root of M star M. Okay. M star M is a positive operator, you can take a square root. And then we can write it as M star M square root times a unitary operator. Okay. And that is the polar decomposition of any operator. It is like writing a complex number as R times exponential I theta. Okay. Such a thing exists in finite dimensions as well. And for anti-linear operator, that equation looks like this. S is anti-linear. So the polar decomposition of S is J is an anti-unitary operator. So that absorbs the anti-linearity of S, but it is anti-unitary. Instead of exponential I theta, I get J, but it is no anti-unitary. That means J star J is 1. Okay. In fact, J squared is 1. It is so J star J is also 1. Multiplied by what is normally written as square root of delta. Delta is a positive operator, which I will find for you. And you write S in the form J delta square root. This you can do all this in finite dimensions. Then infinite dimensions, you can do it under the standard assumptions of quantum field theory, which I will. So you can write it fearlessly for local algebras. Okay? But if you want to prove things, there is some technicality which gives set aside for a moment. So what are these J sets? I think it is an astonishing fact that J acting on an element M, the original algebra, takes it to the causal complement, that is to the commutator. So J transforms the left operator to the right operator. So in a quantum field theory context, it takes the quantum field in some space-time region to a quantum field in the causal complement of that region, which you can calculate. And it turns out that this J is related to the CPT operation. It's not exactly CPT, but close to PT times some rotation. But it's what it is. That's the thing. And you find that this equation has a physical meaning even in that context. Okay?
Gaussian inverse setup does J give you the CPT?
Everything, when I go into quantum field theory, which I will do, we are always working in Minkowski.
But this formula is a generic formula that you can apply this policy.
This theorem is completely general. Okay? So, if you
What happens
yes,
when you go
if you take d theta, for example, it again applies. So it takes you from the right, what do you call it? Right even horizon, right region bounded by the even horizon to the left region.
but there J is not this.
Uh, I, here I'm not sure because I don't know whether CPT theorem applies in d theta. Okay? But J exists.
J exists. But it's I don't
Could be because I am not sure whether there is CPT invariance because in digital or anti-digital. Okay. So I don't know. That's an interesting question. I have not thought about it. See, I have, since we are at this, I have a general issue which is all this. Okay. I think it is good practice to know how this kind of theorem goes forward. But I have no reason to believe that DC or anti-DC this are relevant for local physics. Okay? I'm experimentally I'm doing LHC and what it does is some spectrum of quark or some phase transition. Are they relevant? What is happening in the edge of the universe? I have no idea. There is no evidence. Some people have analyzed it. Okay? My colleague Carl Rosenzweig wrote a paper using Rydberg atoms to see if some distorting the metric for the potential, something he did with a chemical, with some modeling of the cosmological constant changes. You can get some evidence from the spectra of Rydberg atoms. The answer was no. He put very strong bounds. Okay? And there was a debate between him and Steve Adler. I don't know what the conclusion of that argument is. So far as I know, as of now, there is no reason at all. I know okay, that this thing, they're of great practice. They tell that they may apply very well to condensed matter physics. If you put things in a ball, it may suddenly be very useful there. But in standard field theory, the standard LHC experiments, I don't know. Maybe somebody has better insight. I don't know why they are of any relevance. Okay? Maybe Srihari, somebody can tell me. I don't know. Okay? I can't find anything. Okay? Neither, but they don't. People don't address it. They simply do it. I don't know why. I don't see the reason. Okay? Unless it is for academic purposes. Okay? So there's a side remark and also a confession of my ignorance. Okay? But let me go on. Okay? So this J is an anti-unitary operator which shifts you from left to right. Okay? By the way, this can be applied also for representative theory of groups. Okay? And there is again a J. Okay? This I certainly did not know until I came across this theorem. Because you can do a similar construction for the representation theory of the group algebra and you get again a J. Okay? That J corresponds to is transfers you from left action to right action. Okay? So that's an interesting structure, but I have not seen a literature on this. Maybe Amri knows more about it. I'll ask him. But I did not. It's easy to investigate. If you know this much, you can do it. But I simply have not done it. And I think group maths people would have done it. It is such an obvious issue. They would have done it. The second thing is equally remarkable. If I do this decomposition, I'll show it to you. Then this delta is a positive operator. And you can imagine delta to the IT is a unitary operator. And you can generate an auto. You can conjugate the matrix M by delta to the power IT. The remarkable thing is that when I conjugate it, I don't leave M. Okay? I stay in M. So if I write delta as exponential k, this delta to the power IT is exponential ITK, and it conjugates this M, and you stay within capital M. You don't change the algebra. So, but this operator is unbounded and it is not an element of the algebra. Okay? This is coming from somewhere else. Okay? So, it's actually an outer automorphism of this algebra. Okay? It's very strange that it should pop up like this, that intrinsically it should pop up like this. And this is the operator which comes up as the, if you do the Riddler wedge, this K is the thing that comes up as the boost operator, giving you the trajectory of the accelerated particle. Okay? Just come out of nowhere, okay? Purely from the fact that the cyclic and separating vacuum. And this K is what is called, we call as the modular Hamiltonian. Okay? The modular Hamiltonian is not the real Hamiltonian. The time evolution given by the modular Hamiltonian is not the real time evolution. The real time evolution, if there is some Hamiltonian for the whole system, I'm doing matrices, so I didn't give you the dynamics of evolution. That is something else. Yeah. You can write it, but that is not this K. Okay. So you may ask, what is this K2? I wish I knew exactly. It appears to be, this is a guess. It appears to be, as time evolves, it is measuring the entanglement between the vectors. See, I started from a vector, which I called omega, where there is a strong entanglement between left and right. Okay? It was a tensor product of left and right and sum. And this operator, exponential ITK, as time is progressing, is disentangling that entanglement. Okay? It appears to be disentangling, and entropy keeps increasing. That I can prove. That the entropy keeps increasing under this evolution. It appears to be disentangling the vectors. So it appears that this pushing the system more towards a classically completely disordered system. Okay? It appears. Okay? That is not what your standard Hamiltonian does. This appears to be what this is doing. Okay? But this is an issue that has to be investigated carefully. Okay? If you like, I can tell you about my thoughts on the Riddler wedge. There are some very interesting things happening there. Or in QCD, if there is time, analogous phenomena happen. So we can talk about it as we keep going. Okay? Sorry?
So from the maps we understand disorder is coming, but we don't really understand. So you said that the model of flow brings in some sort of disorder in the system.
It appears, what I can show, what I can show is that because of the fact that I'm changing the dual, so this, notice that this delta, I'll write a formula for this K. Okay? You see that K acts on both left and right. Okay? It is so, it is not in the algebra. I'll give the formula for K. Okay? So it is changing the basis in the left, on the right. But if you change the basis, in the notes I gave last time, or maybe the entropy will go on increasing. Okay? So that is a purely kinematical effect of property of algebraic convex figures. Okay? So if you have a convex body, this always will happen. Okay? This is Jensen's theorem. Okay? So it will go on increasing. Okay? In infinite system, in finite system, you have n bits, qubits or whatever it is. Presumably, once upon a time here, I checked what is the fixed point of this algebra, because it's evolving the entropy, and you find that this Boltzmann point, that is, the entropy approaches log n. So you can write a generic formula for this entropy using this stochastic maps, quite easy. Vary it and see what is the maximum. You find the entropy answer of Boltzmann. Okay, that is easy to prove. But in infinite system, can't be that every vector of the Hilbert space is getting mixed. You're getting all the terms of the Hilbert space, okay, with coefficients in the expression. Immediately it will diverge. Okay, if you write density matrix like AI, rank one density matrix, for all the vectors of the Hilbert space. With equal coefficients, you take trace, you'll get infinity. Okay. Right? It will be the unit operator in the Hilbert space. Infinite dimensional. It will be infinite. Trace will be infinite. Cannot be density matrix. So that cannot be right. So where is it going? I don't know. I think it will never thermalize. In a physical system, that kind of thermalization seems impossible. What Boltzmann was only doing, I suppose, finite many, what he would call degrees of freedom. Here, I don't even know what is meant by degrees of freedom. I don't really understand. It appears to be, how do I count? How many, what do I mean by suppose I have n fields in some space-time region acting on vacuum. How many degrees of freedom are there? I don't know. N, it is dense in the full Hilbert space. Is it n or is it infinite? I don't know. I think that language seems misguided. At least I don't understand it. And it gives wrong answers also in particular cases. So, yeah. What was your question? I think
I was asking, like, do we know the physics? Why is no generation solved? From maths, you can see some sort of entropy. You know the similar reason.
Yeah. The one paper which I found, I don't know, but the one paper I found is a paper by Raphael outside the black hole horizon or outside any event horizon, where he writes out the condition that if the entropy steadily increases to this towards the value we may expect by equal occupation of all the states, then he gives an argument that the entropy for if it goes towards that, so the flow is towards that value, then the entropy will necessarily increase. So he gives an argument that the black hole entropy will steadily increase in a paper that he has written. That is one concrete statement I have found. Okay? Last time I came, I thought, I don't understand, something is going on. I should get some really good mathematicians. The reason is, I thought that this entropy increase may give a direction of time, right? Because I can say that's what both people have been writing all over the place. Is it true? No, not in this way, because I could evolve by not delta the IT, but delta the power of minus. I can reverse the T. Okay? I will again increase it because Genesis theorem doesn't care which way you go. Okay? So something else has to be done. Okay? Now, here I am going far ahead. I don't know the answers. We will see that all local algebras are thermal, and it is exponential minus beta times this k times observables. Okay? The trace of that. So the thermal Hamiltonian in all local algebras is a KMS state, but the k will change from place to place. Okay? Now evolve it in time. K is coming in the thermal state with exponential minus beta k, no I. But evolve it in time, I will multiply the operator by exponential it k and conjugate. So you can rewrite k, you can rewrite beta to absorb this extra t. So what happens is that beta becomes complex. Beta plus it you get. Okay? But we know from the other theorems that in the thermal state you can extend beta to a strip in the upper half plane, but only in one direction. Okay? You can go either depending on the signs of the problem, you can go only in one direction in a particular strip. The other boundary, actually you get crossing symmetry, you get saved some conformality theory. This has been known for a long time. You go to the other end, there is this activity using this some conformal field theory actually. Okay, this half-sided model recursion. You're the one who were talking. That you get some conformal field theory, it has been proved, but only in one direction. If you go the other direction, it will blow up. Is it giving me direction at time? I don't believe it. I just conjugated it and I get beta complex. So what is beta is complex? In particular direction, depending on the sign I choose for t. Which sign does it give a direction at time? Because by using analyticity, I doubt it. Something is wrong in my statements. I don't. Well, I have not traced what is wrong. So I am waiting for my Russian friend Sasha Pinzul to tell me what is wrong because he can prove these theorems. I can't. I have some notes on how to prove it, but they are not trivial. Cohn, others have proved this analyticity in the strip is not easy to prove. All these theorems of Lin-Yang theorems, zeros, all these are coming from this analyticity in the strip. And so the maths people knew it. But if I look at the maths book, it is quite difficult. They are not trivial proofs. Something is going on here which we have to understand. So, but we are digressing. So I want to tell you what this S is. So let me calculate S. This is the what they call the modular involution. It is operator which is anti-linear involution. It is not unitary. It is in fact unbounded in the quantum field theory case. Necessarily unbounded. So the K that people write in all this language, people working with string theory, they write this modular Hamiltonian and so on. They cannot be the true Hamiltonian ever because they are unbounded below and above. There is no way you can make it bounded. If you make it bounded, you have changed the algebra completely. This is not a type 3-1 or you will violate causality, all kinds of things will happen. So that is not Hamiltonian, but that is what comes into play here. So I'll tell you how to calculate it. It's rather easy. You take AJ, this operator, and it is anti-linear, I told you. So take AJ star and actor on the vacuum, there's nothing. Yes, I put S through, I get AJ star, I get ASG. I told you that the star of this operator is. Okay. So let me see how.
S is the computer operator.
S is the Tomita operator. On a generic vector, I can get all vectors of the Hilbert space by acting on the cyclic separating vacuum with AJS. So I check what happens with the AJS. S conjugates the operator. It's anti-linear. AJS is not a real operator. Real, what do you mean? N by N matrix is real. What does it mean? No.
Then can you write this?
No, I am not assuming that. I gave an operator AJS acting on omega, which does something on the vectors. I didn't say A is Hermitian or anything. By definition of S, S is anti-linear.
I get the first part. Second part of the
So S, AJS, S inverse, S omega. So S on omega, the Tomita involution S is identity on your cyclic and separating state, which I should have said, but you see it emerging also. So S active on omega is 1. So a conjugate AJS. The conjugate AJS with S is anti-linear. So Hermitian operators will go to Hermitian operators, same. And with the, if you write AJS as AJS plus AJS star plus I times AJS minus AJS star divided by 2, one will remain the same, I will go to minus, right? So the action of S on any linear operator is AJS star. By definition, because it is anti-linear.
that part is okay. I'm asking, you are writing something else. You are writing it as ASJ.
That's because I showed before that the star of this is this one. I proved it by explicit calculation of what it meant by adjoint. Yeah. So you remember this, just simply I took scalar products and check. Okay. So here is a calculation I have given to prove this. I can skip it because you simply check that yeah, I am going to write this out explicitly. So S is acting on so I omitted the cat symbol and S is acting on this vector. So I am told that this is equal to the Sj, which is this. Okay. So this is equal to this. That's what the equation says. Or S acting on this. Let's keep this in mind. This is an important equation. Let us keep this in mind. So you can see here how this is getting manipulated. And the issue is what is J. If I know J, I can find delta and check whether in fact it is a positive operator. And is anti-unitary. So up to a phase, but which I can choose one. I will just say that J acting on my basis vectors is simply flips the inverse. So I will simply say that J acting on Fj is Fjgs. This is clearly unitary on these vectors because it is simply the scalar product of these vectors is not changed. And I extend it by anti-linearity on the full Hilbert space. So if we take linear combinations of this with complex coefficients, they will all get complex conjugate. So this is the definition of J. I choose it and let us see whether we get a consistent answer. So I want to calculate delta to the power of half. So delta to the power of half, remember that S was like this, and I want to I have given a formula for J, and I want to compute delta to the power of half. But J squared is 1. J is anti-unitary involution. So J squared is 1. The definition also says J squared is 1. So delta to the power of half is J times S, which is what I wrote here. Delta to the power of half is J times S. So I know J and I know S. I calculate delta to the power of half. Okay. So delta to the power of half acting on AJ FSJJ, with J acting on S. So we have already said what S. How do you go? And confused. Did it define S? Yeah, of course. S is the complex conjugation operator. So this is J times S. So yes, this A's are sorry. Here it is. A's are real. That's important. Because it's a linear A squared, it's a positive square root of A squared. So S acting on this will not change the change and then S will take F plus Gj to Fjgs. Okay. So you see that delta to the power half is given by this J times this. So J I told you, and again S's are real, so you simply flips in this, you get F plus times Gg. So I know what is delta to the power half. Okay. So delta to the power half or F plus Gj is equal to, by comparison of the two equations, AS over AJ times this. Okay. This is a very important equation. So these vectors Fx times Ga are diagonal in square root of delta. Okay. With eigenvalues AS over Gg. So delta has eigenvalues AS squared over AJ squared, AS over AJ squared. So it is a positive operator. This square is all positive, so it is a positive operator as we want. And furthermore, when S equal to J is 1, so in the vacuum, what I call omega, these two indices are equal. So this becomes 1. So the vacuum is an ideal state with eigenvalue where delta doesn't change. So delta leaves the vacuum invariant or its logarithm, we call it modular Hamiltonian, is zero on the vacuum. This is so, and it is notice that it's acting on both left and right. Okay. So this operator acts, it's not an operator in the algebra, okay, because it acts on both left and right. And it is very important because of the fact that you want the vacuum to be invariant. So that is guaranteed by this equation here when S is equal to J. The vacuum vector was some AS, FS, CS times AS summed over, and that is invariant. So vacuum is invariant. Why is it important? If you go back in Hart's book, he emphasizes a lot that you need this separation because of the fact that otherwise you will not have the thermodynamic, say, quantum field theory context. So the fact that you have this additional thing coming from the right renormalizes your eigenvalue of K, and it enables you to have a thermodynamic limit. You remove it, it will blow up. Okay? It will blow up when we go to the thermodynamic limit, and he shows it. And it has been known for a long time to this gang of Haag, Higgenholz, Lieb. These people knew it. It maybe, yeah, they knew it quite well. I mean, for a long time, I would say decades. So, so I said here that the vacuum is invariant. So delta K is zero on the vacuum. The modular Hamiltonian is zero on the vacuum. It is not in the Riller way the boost operator. It is boost operator on the left minus the boost operator on the right. Okay. So boost operator in one Riller wedge minus the boost operator on the left Riller wedge. Okay. So in one case, the particle is accelerating in one direction, the other way is going the other way around. Okay. So there is a sign change which enables them to cancel. And it is quite important to have a consistent finite theory. Okay. So I have given here. This should be, this should be not K, it should be delta. Right? This K should be delta. Okay? And or this is, if you have K, there will be a logarithm here. Okay? So delta K is a logarithm of delta, there will be a logarithm here. So when it's equal to K, you get zero again. So for what we call the modular Hamiltonian, you get zero eigenvalue. But for the modular operator, you get 1 as the eigenvalue. Okay? So that is just a side remark. Okay. This is a side remark. If I write this delta as a something acting on the one side left minus times something acting some other operator acting on the right with an inverse, because of the fact that you get the denominator here, you see that rho and sigma are unitarily equivalent. Okay? So if you think of rho as some density matrix acting on the left, then sigma is a unitarily equivalent density operator acting on the right. Okay? But you have to write the delta then as rho times sigma inverse. Okay? The inverse is the whole story hangs by the inverse. And because of the complexities of this activity, as I told you earlier, you get first divergence cancellations and you then get general formulation. Sorry. So I think that, so this is what I wanted to tell about today. And I think I did send Gayatri my next talk, which will be directly getting into quantum field theory. What are the problems in relativistic interactions already in relativistic interactions already on particles? Okay. We will recall or outline the problems, impossibility of mentioning causality among relativistic point particles, and we will go on to see how it gets resolved when we go into quantum field theory. So we will see that the standard interpretations of quantum mechanics, like Bohr's interpretation of wave functions, are not right in the context of quantum field theory. It simply doesn't work. It's simply wrong. Non-relativistically, it's a different issue, but when one goes into quantum field theory, it is simply not right. And I'll tell you why it is not right. Why it will violate causality and how it has been resolved. I'll tell you. Next time I'll do it. Okay. Maybe I should stop here. Yeah. And we can continue. Okay. So I wish Ramachandran was here. Okay. He told me his daughter studied under Ullas.
I am here.
Now you are here.
Yep.
Yeah. Good. He told me that when Ranjini, his daughter, went to study music with Ullas Kashalkar, he told her to forget everything you have learned before and start from the beginning. Here too, when you come to this mode of thinking, forget about all quantum mechanics you are taught from chapters of some book. Start from the beginning, because many new things are happening. So that will be my focus. Or another quote that I remember is, if you have had occasion to read Dante, that Divina Commedia. So there's a big sign in front of the hell, says, abandon all hope, all who enter. Likewise, you abandon all hope, all who enter this fortress of quantum field theory, because it is truly extremely complicated and rich. So we'll continue with that next time.
The chapter
About what?
the family.
Oh, you can, sorry, I don't remember the chapter, but if you look in the index, you will find it. It is there. Okay? It is one of the things that look at the KMSCs. He discusses what happens, and he talks about thermodynamic limits, and also he talks about simplexes, whether the KMS is forming simplex, is there a unique entropy, what is the physical meaning? He discusses all this. So some of it I will try to cover. Okay? Much of it I am as much. My grip is as weak as any of you, so we can do it together. Okay.